In Unit 5 of Bmath 048, you're going to learn how to make box plots. In fact, you're going to learn how to make two types of box plots, the basic box plot and the modified box plot. Modified box plots giving a bit more information. And once again, what we're trying to do in this part of our statistics course is to take a bunch of numbers and organize them and try to express these numbers in a picture. So that's what the box plot is all about. First, I'm going to show you how to capture data from the Word document, and if you have it as a PDF, make sure you save it to a drive and open it up as a Word document. So I'm going to capture data from this Word document and dump the data into a box plot generator. The box plot generator is located in the Bmath 048 Moodle course in Unit 5. So I'm going to actually demonstrate how to capture the data that was used in generating the all beef hot dog in the video. So here's the data. It's already actually been ranked for us. 20 different brands of all beef hot dogs. I'm going to left click on one of the terms and drag my mouse, highlight all the terms, let go of the left mouse button, click the right mouse button, and press copy. And then I'm going to paste that information into the box plot generator. In Unit 5 of Bmath 048, in the Moodle course, you will find the section on box plots. There's a student guide that you need to download. There's solutions to all of the exercises in Unit 5 as well that you need to download. First thing you should do is really watch the video, however, on box plots. There's also a Moodle quiz in Unit 5 on box plots. Now, further down in the technology component, there's a box plot generator. I'm going to select that now. The generator is opening up. I'm going to maximize my screen. And we want to actually get our data into the plotter, but I want to actually select sample because we have less than 1,000 data entries. Now I'm going to click in the field for entering the data, and you only need to push commas in the field to separate the data if you're typing it in, but I'm just going to paste it. So I'm just going to right click, hit paste. There's all my data, submit the data. Oh, and there's the box plot. So this is the same box plot we saw in the video. And we have whiskers at the either end. The hot dog data is circled here in yellow, and that's the caloric data for 20 different hot dogs. Now, that information was used in the software to generate a box plot, and in this box plot, we can identify what's called a 5-number summary. A minimum value, the value of the first quartile, Q1, Q2, or the median, Q3, the value of the third quartile, and the maximum value. Those 5 numbers give us the 5-number summary, which allows us to do a sketch of a basic box plot. To calculate Q2, the median, it's what you've learned previously, where you take the number of terms, add 1, and divide by 2. And that's how you calculate the median. The interquartile range, the IQR, is given or calculated by taking the value of the number that is the third quartile and subtracting the value of the first quartile. That gives you the interquartile range. Right. So let's say we have some grades in an exam that are displayed in a STEM plot. And these grades are, well, there's 20 of them. So I want to find the position of the median, the second quartile. Well, that's going to be given by n plus 1 over 2. Well, that's going to be equal to 20 plus 1 over 2, which is 21 over 2, 10.5, which means that the position of the median will be between the 10th and 11th term. So what you can do, in fact, is divide your data. If you've got 20, yeah, there's 20 data values. Divide them into a lower half and an upper half. If you've got an even number like this, it makes it easy. And what is the 10th value? Well, the 10th value is this one, and the 11th value is 82, which means the median is going to actually be the average of 82 and 85. And so the median will be 83.5. And that would be the value of the median. So if the data has been divided into upper and lower halves, we can then work in each half separately. To find the position of, say, Q1, the first quartile, what I'm going to do is I'm going to look at the lower half of the data. Now, when I separated the data into two halves, the lower half has 10 terms, so the location of Q1 will be n plus 1 over 2, which is going to work out to be equal to 10 plus 1 over 2, which is 5.5. So between the fifth and the sixth term, between term 5 and term 6. So where are those? 1, 2, 3, 4, 5. There's the fifth term. There's the sixth term. I'm going to average those two to get Q1. So Q1 is going to be equal to 72 plus 76 over 2. Well, that means Q1 is equal to 74. For Q3, I'm going to do the same thing. Q3 is going to be midway between the ends of the upper half. So Q3 is going to be there. That's going to be the average of 88 and 90, which is 89. So now I have really a 5-number summary. My minimum value, let me just highlight it. There's my minimum value. There's my maximum value. I know my Q2. The median is 83.5. Q1 is 74 and Q3 is 89. That information allows me to calculate or to create a box plot. So here's a 5-number summary of the box plot I just constructed, or that I could construct using that information. I know my minimum value, the value of my first quartile, my second quartile, which is the median, the third quartile, and the maximum value. Filling out the information for the 5-number summary. I have created a little chart like so, and using that chart, I can create a box plot. Notice that this box plot is very skewed. There's a really long whisker at the low end, and it's really unclear, is that whisker due to having a whole bunch of data scattered evenly between the minimum and the first quartile, or is it just due to a few numbers just as kind of maybe outliers hanging in there just around where the minimum is, and that's creating that skewed picture. In other words, did most people do pretty well on the test, and a couple of people just got in the like 40 or 41, and everybody else was doing very well? Or is there a large spread between the minimum value and Q1? Are there a lot of people grouped in that area? In order to do that, we need to look at a modified box plot. Modified box plot gives more information than a standard or basic box plot. Really, the first thing you need to do, if you have not already done so, is to calculate Q1 and Q3. Once you've done that calculation, you can then calculate the interquartile range. The interquartile range is equal to the difference between the value of Q1 and the value of Q3 and the value of Q1. Once you've got the interquartile range, you can do 4 more calculations. These 4 calculations involve calculating what are called fences. So with the modified box plot, 2 types of fences: inner fences, outer fences. The inner fences, the way you calculate them is you take the interquartile range and you multiply that by 1.5. Then what you do is to calculate the lower inner fence. So by the lower inner fence, I mean this is going to be in the direction below the first quartile. So the lower inner fence is going to be calculated by taking the value of Q1 and subtracting 1.5 times the interquartile range. Now, to calculate the upper inner fence, in order to do that calculation, you take the interquartile range, multiply it by 1.5, and add it to Q3. I just want to point out in your notes, they have it wrong. So you add 1.5 times the interquartile range to Q3 to get your upper inner fence. And now the lower outer fence and the upper outer fence, they're calculated the same way, except instead of 1.5 times the interquartile range, you're going to multiply the interquartile range by 2 in both cases. Next, you draw a modified box plot using the median Q1 and Q3. Now, I suggest you take a scale into account so that that you can plot outliers if necessary. Now, outliers are values that are between the, let's just take an example. So in the modified box plot in your notes, here I'll expand it a bit so we can look at it a bit better. In the modified box plot in your notes, I've indicated the location of the inner fences. Now, these were test scores, and we have to assume the maximum score you get was 100%. So we're going to assume these test scores have a maximum of 100. So the upper inner fence and the upper outer fence don't really count because you cannot get a score over 100. However, people can certainly get scores less than 100% on a test. So what you do is you draw the basic box for your box plot, include the median, Q1 and Q3, and now you've got to find some whiskers. Well, because in this case, the upper inner fence is beyond 100. Now, the calculation they've shown you for that is up here. They've got the fence calculation. Here's the inner fences. So for the inner fence, you've got 50. The lower inner fence would have a value of 51.5. The upper inner fence is 111.5. 111.5 is greater than 100, so you're not going to have any scores that actually reach the upper inner fence. So you're going to simply take the maximum score in your ranked data set and use that maximum to get your upper whisker. Same as the basic box plot. However, for your lower whisker, what you're going to do, you're going to identify the smallest data value, which is between Q1 and the lower inner fence. The smallest data value between Q1 and the lower inner fence will get you the whisker down here, your lower whisker. That's going to be the smallest data value, not greater than the inner fence. Now, in the data that we provided, there were two test scores, 40 and 41. Those test scores are beyond the lower inner fence. They are outliers. And those outliers, we're going to indicate those outliers with asterisks. So these students, because they were located, their test scores were located between the lower inner fence and the lower outer fence, we're going to call those scores outliers. However, if somebody had gotten, I don't know, 10 on the test, they'd be like way over here somewhere. What you do is you make that a hollow circle, and that's really what's called an extreme outlier because it's beyond the outer fence. So with that kind of description, the modified box plot allows you to get more information from the picture, because not only do you have a box plot that has whiskers, you have a box plot where you are pictorially representing data which is an outlier or even an extreme outlier. And the accepted standard is that any data which is more than 1.5 times the interquartile range, either added or subtracted to one of your quartiles. So for example, the lower inner fence is the value of Q1 minus 1.5 times the interquartile range, and that gives you your lower inner fence. The upper inner fence is Q3 plus 1.5 times the interquartile range. Any data values that are between the inner fences and the outer fences are outliers. Any data values beyond the outer fences are extreme outliers. Okay, 5-number summary of this distribution. Well, the first thing I had to do was rank it from smallest value to largest value. And the first thing I'm going to do is find the median. So the median, or the words Q2, the position of that is given by n plus 1 over 2. Well, there are 20 terms. That's 20 plus 1 over 2. So that's 21 over 2, which is 10.5. So that means the median is located between the 10th term and the 11th term. So it's kind of, here's the 10th term, here's the 11th term, and so it's going to be the average of those two. So Q2, the median, is going to be 152 plus 153 over 2. So the median is actually 152.5. So now I need to find the first quartile, Q1. Well, Q1 is going to be, again, halfway between the 10th value and the start. So how many values do we have here? Well, the median is actually, 152.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So halfway down the middle here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It looks to be that 139 is Q1, because you have 1, 2, 3, 4 values on the left side and 1, 2, 3, 4, actually 5 values on the right. I got 10 values. Actually, I have to, well, that means I have to actually find the average. I have to find the median now of the lower half of the data, and that's Q1. So Q1 is going to be equal to, there are 10 terms in the lower half of the data. So Q1 will be n plus 1 over 2, which will be 10 plus 1 over 2. 10 plus 1 is 11, 5.5. So let's count the terms. 1, 2, 3, 4, 5. The average of those two terms is going to be Q1. So Q1 actually will be equal to, the average of 139 and 141. Well, that's 140. So Q1 is 140. Now I've got to find Q3. Well, Q3 is going to be, Q3 is going to be the median of the upper terms. Well, what do we got? We got 10 terms, so Q3 is going to be equal to n plus 1 over 2. So it's going to be equal to 10 plus 1 over 2, which is 5.5. So, well, starting here, find the fifth term. 1, 2, 3, 4, 5. Okay, and there's the sixth term, so the median of the upper set of numbers is going to be there. So, well, what is that? That's going to be the average, the numerical value of Q3. This is just the position of Q3. It's the fifth. It's between the fifth and sixth term. The actual value of Q3 is going to be equal to 176 plus 181 over 2. Which is 178.5. Well, I can actually do my 5-number summary. Here we go. I'm just going to make up my. Well, the minimum value was the first value in the ranking, which is 111. Q1 I calculated here to be 140. Q2, the median there is 152.5. Q3 I calculated to be 178.5. And the maximum, let's look at the ranked data, the maximum is 190. Okay, so there's the 5-number summary. I think I've explained how I got to the answer. Okay, calculating the range and the interquartile range. So the range is simply the difference between the maximum and the minimum values from the data. Well, from our 5-number summary, we can take that. The range is equal to the maximum minus the minimum. So from the 5-number summary, that's going to be equal to 190 minus 111. Well, the range then is 79. Now, the interquartile range, however, IQR, the interquartile range, is Q3 minus Q1. And that is, Q3 is 178.5 minus Q1, which is 140. So the interquartile range is, that's 38.5. So that what these numbers do is, in terms of talking about variability, the range is just this, the distance between the largest and the smallest values. The interquartile range tells you how tightly grouped the data is. So because each quartile is taking into account kind of the spacing of the data. So the interquartile range is like how tight are they grouped together? How spread out is the information, which is more information than just the straight range. So would a beef hot dog with 175 calories be in the top quarter of the data? Well, Q3 actually is 178.5. This means that 25%, or 1/4 of the data, has values greater than this. So a hot dog of 175 calories is a data value between the median and the third quartile. Keeping in mind, the median splits the data in half, so that 50% of the data is above the median, 50% below. The third quartile, 25% of the data is above the third quartile, 75% is below. So the calorie with the hot dog with 175 calories is in the collection of data that's more than 50% of the data, but less than 75% of the data. And so in order for that hot dog to be in the top quarter, it would have to have more than 178.5 calories, maybe 180, 200. Well, actually, they were not at 200, 190, but it would have to be more than 178.5. Well, I'm going to use a box plot generator to draw a basic box plot for the calories per hot dog. So I'm going to go to my Word document. I'm going to highlight the hot dog caloric data. I'm going to copy it. I'm going to go to my box plot generator and select a sample and I'm going to paste in that information. There it is. And now I'm going to submit data. And where's the box plot? Where's the box plot? There it is. There's my box plot. Ooh, yeah. Okay. So there's the box plot. All right. Here's the basic box plot. And I'll just label some items. Well, let's just make it a bit bigger to see the scale. Oh, look at that. Okay, so this is the low end. And that's Q1. This is the median, otherwise known as Q2. That's Q3. Okay, this is my maximum value. And this is the minimum value, 110. Remember, the maximum was 190 calories. The minimum was 111. Okay, so there. So I've got the box plot. And really, I could fill in my five number summary, but I'm not going to, because what I am going to do now is look at the next question. So which is, in which quarter, the first, second, third, or fourth, is the data most concentrated? Well, looking at the box plot, this here, this range of values is, it's about the same as that range of values. It's pretty big. So what we need to do is we need to compare the range of values between the median and Q1 and the range of values between the maximum and Q3. You see, the range of values between Q1 and the median, well, that's the range of values that's between 25 and 50% of the data. The range of values between Q3 and the maximum is the range of values between 75% and well, the rest of the data. So 100% of the data. So this is the between Q3 and the maximum is the top 25% of the data. And those, they look pretty similar, but let's just calculate the ranges. So I'm going to find the range between the median and Q1. So the range median minus Q1. So this range, A, call it, will be equal to the median. Well, the median, the value of the median from our 5-number summary was 152.5, and Q1 was 140. So this is going to be 152.5 minus 140. That's 12.5. Okay, let's look at the other range. Call it range B. And that's going to be between the maximum value and Q3. Well, let's get the numbers. Well, the maximum value is 190 and Q3 was 178.5. 190 minus 78.5. Oh, well, what's that? That's 11.5. Okay, so this range is tighter. So that means the data is most concentrated here. That's where it's most concentrated. Because that's the smallest spread of the data contained within 25% of the data. So once again, between the minimum and Q1, that's 25% of the data. Between Q1 and the median, that's another 25% of the data. Between the median and Q3, that's another 25% of the data. And between Q3 and the maximum is the final 25% of the data. The data is most spread out. Will probably be between the minimum and Q1. We're not asked to calculate it, but that distance here looks bigger than that distance. The data is most concentrated, though, between the maximum and Q3, because that's got the smallest range. Oops, as it turns out, well, we want to find out where's the data most spread out. Well, what I'm going to do is I'm going to look at the box plot and go, okay, well, it's going to be either between Q3 and the median or Q1 and the minimum. So let's just get those. From our 5-number summary, we see that Q3 is 178.5, the median is 152.5, Q1 is 140, and the minimum is 111. All right, so I found Q3 minus Q2, that's 26. So Q3 minus Q2, that's this here. That's Q3 minus Q2. And I also calculated Q1 minus the minimum, which is this. Turns out that Q1 minus the minimum is a bigger number, 29. So that's where the data is least concentrated. Here in this region, data is less concentrated. Okay, so in order for us to find if there's any outliers, we have to multiply the interquartile range by 1.5. So first of all, let's calculate the interquartile range, which is going to be Q3 minus Q1. Now Q3 is equal to 178.5 minus Q1. Q1 is, well, 140. So that's the difference of 38.5. That's your interquartile range, or IQR. So now what I'm going to do is I am going to find my lower inner fence. And I'm going to find my upper inner fence. The lower inner fence is going to be given by Q1 minus 1.5 times the interquartile range. The upper inner fence will be calculated by going Q3 plus 1.5 times the interquartile range. Okay, I'm going to calculate these. So Q1 was 140. So this is going to be equal to 140 minus 1.5, those in brackets, times the interquartile range, which is 38.5. For my upper inner fence, this is going to be equal to Q3, which is 178.5 plus 1.5 in brackets times the interquartile range, which is 38.5. Okay, let's calculate. So the lower inner fence then turns out to be 82.25. And the upper inner fence turns out to be 236.25. Well, none of the data extends out to these fences. The smallest data value was 111, so there are no outliers in the lower half of the data. And the largest value was 190 calories in the data set for hot dogs. So since the upper fence is 236.25 calories, well, there is no data that is on either side of those fences. So there are no outliers. So I'm going to copy the data from exercise 1 and put it into a stem leaf plotter. Copying the data, going to a stem leaf plotter. Here we go, the stem leaf plotter that's in your Moodle course. I'm going to paste the data in. There it is. Doesn't matter if it's ranked or not. Generate a stem plot. And there it is. There's the stem plot. Well, here's the stem plot. And notice that the data is kind of grouped. There's like a group down there and a group up there, and there's kind of a gap between the groups. So there were no hot dogs at all that had calories, 160, basically between 159 and 174. There were no hot dogs with those values. So there's quite a gap where there's, no information, no hot dogs were produced with the caloric values in the gap. You don't see that info in the box plot. Also, it kind of suggests, looking at this, that this low value down here might be an outlier. But if we use the 1.5 times the IQR, subtracting that from the value of Q1, you can see that the lower fence was like way down here somewhere. There's where the lower fence was, or the inner fence, I should say, for the lower data set. So technically 111 is not an outlier. It looks like it's separate from the main groupings. So probably a box plot in conjunction with the stem leaf plot, or a modified box plot even in conjunction with the stem leaf plot, is kind of a good way of looking at a collection of data because both techniques complement each other. So question 4 gives some data for 20 brands of veggie hot dogs, and they're already ranked. So what I'm going to do is I'm going to make a 5-number summary of the veggie dogs. The location of Q2 is given by the formula n plus 1 over 2. That means the location of Q2 is 20 plus 1 over 2, 10.5. So Q2 is the average of the 10th value and the 11th value. So the 10th value is, in the rank data, is 60, and the 11th is 70. So the value of Q2 will be the average of 60 and 70, which is 65. In the bottom half of the data, in the lower 50% of the data, there are 10 data values, and that means if we count in, well, the location of Q1 is going to be located between the 5th and 6th data value. So 1, 2, 3, 4, 5, 6. That's where Q1 will be. So, well, the average of 50 and 50 is just 50. So Q1 is 50. Q3 is going to be the average of the 5th and 6th data values in the upper 50% of the data set. Or if you want to count the whole data set, the 15th and 16th values, which are those two. So that's Q3 is going to be equal to the average of 90 plus 95, which is 92.5. The maximum value is, not my maximum, minimum value is, the maximum value in the data set is 190. The minimum value is 40. So now I'm ready to make my 5-number summary. Well, so now I've got my 5-number summary. The minimum value is 40. Looking at the data, 40 is the minimum value. Q1 is 50. Q2, the median value is 65. Q3 is 92.5, and the maximum value is 190. Well, now question B is to make a modified box plot of the veggie dog data and identify the outliers and extreme outliers. Well, I'm going to do that now. All right, so let's make the modified box plot for our veggie dogs. So you can see here's Q1. Here is Q1. There's the median. There's Q3. And now we need to identify where the whiskers go. I've already got them on the box plot. I'm going to explain why they're there. Notice at the lower whisker, the whisker below Q1 is at 40. Well, let's take a look at our fences. Well, the inner fences below Q1 minus, well, 68.75, because that's what 1.5 times the interquartile range is. You see, the interquartile range is the difference between Q3 and Q1, which is 42.5. You multiply 42.5 by 1.5, and you get 68.75. So for your inner fences, that's what you're adding or subtracting to your quartiles. So for the lower whisker, for the values below Q1, you take Q1, subtract 68.75. Well, 50 minus 68.75 is 0. Well, you can't have like negative calories with a hot dog. So realistically, the smallest value that we can have for our inner fence is 0, and that means that the smallest value we can have for our outer fence is also 0. Now the outer fences are 3.0 times the interquartile range, so 3 times 42.5 is 127.5. Wow, okay. So for our inner fences, well, you're going to go Q3 plus, well, 1.5 times the IQR gives you 161.25. So that's your inner fence greater than Q3. And the outer fence greater than Q3 is going to be 127.5 plus 92.5, 220. So here's the data. And so we're going to put the lower whisker on our modified box plot by deciding if the smallest data value, like what's the smallest data value in our set that is not greater or that's still within the inner whisker. So since the inner whisker is 0, 40 is the smallest value in our data set that is still inside the inner whisker. So 40 inside the lower fence. So 40 becomes the lower whisker, which I've indicated on the modified box plot. Looking at the data, 110 is the smallest data value that is within the inner whisker, which is greater than Q3. So the inner whisker is 161.25. The data value 110 is less than that. However, the data value 190 is more than that. So 190, the value 190 lies between the inner whisker and the outer whisker. So it is a mild outlier. So 110 is the upper whisker in our box plot. And the data value 190, way out here, this I'm going to indicate by an asterisk. So the beef dogs, the beef dogs are ranked from smallest value to largest value. And there's a 5-number summary that I've created for the beef dogs. The interquartile range is 38.5. Done some calculations to establish the fences. 1.5 times the interquartile range is 57.75. There. 3 times the interquartile range is 115.5. So for the inner fences, Q1 minus 1.5 times the interquartile range. Well, Q1 was 140 minus 57.75 is 82.25. The upper inner fence is Q3 plus 1.5 times the interquartile range. Q3 was 178.5 plus 57.75 is 236.25. Those are our inner fences. Let's see if there are any outliers. In other words, we're looking for data values outside of those limits. Looking at the data. Well, what about the lower fence, 82.25? Well, the smallest value is actually 111. So, well, that's going to create a whisker. So that's going to be the lower whisker because it's not smaller than the outside the inner fence, the inner fence that's below Q1. What about the other way, 236.25? Well, the largest value is 190, so there's no outliers because 190 once again is less than the inner fence above Q3. So I can just go ahead on and create a box plot for this then. So there are the two box plots. The veggie dogs seem to have fewer calories as a group than the beef dogs. However, looking at the whiskers, the upper whisker for the very veggie dogs is almost the same as the lower whisker for the beef dogs. So some veggie dogs have um, quite a few calories, and you could read the discussion in the um, answer guide. You should, however, note the outlier for veggie dogs. The outlier for the veggie dogs is almost as fattening, almost does as many calories as the beef dogs do. Anyhow, there's the data, and that's it. So there's the modified box plot for beef dogs. There are no outliers. Well, sorry, there are no outliers, and the uh, smallest data value, since there was no outlier, the smallest data value is a whisker, and the same with the largest data value. The largest data value in our modified box plot for beef dogs is the upper whisker, because the whiskers, the inner whiskers for these beef dogs, were believe it. So here's the modified box plot for beef dogs. Notice that the whiskers for the beef dogs are actually the same as the minimum and maximum values for the basic box plot, because with the beef dogs, when I calculated 1.5 times the interquartile range, what happened was, for the beef dogs, we ended up with inner fences of 82.25 and 236.25, and none of our data values were outside of these inner fences, which means that the minimum and maximum values that we had in our data for the beef dogs actually are the whiskers. Note that the veggie dogs had a outlier, and that outlier actually had a high caloric value and really matched the calorie count of the highest calorie beef dogs. So visually representing data is a useful tool to help analyze many problems. So now it's your turn.